Hi, I'm Mr. Sapone, and I'm bringing you a screencast on unit conversions and dimensional analysis. Sounds very complicated, but it's not really. In this presentation, we're going to look at units, and we're going to ask what are units, why are they important, we're going to look at some famous unit conversion errors, we're going to look at the dangers associated with not using units, and then there'll be a brief assignment at the end for my students. Um, And there is a warning down on the bottom. This is generally true. You want to avoid doing unit conversions if you enjoy making mistakes. You have a phobia of correct answers. You enjoy solving problems in a very convoluted manner. You take pleasure in reinventing the wheel. Or you're just generally a very bad human being. If you're a bad person, you will not like unit conversions. If you are a good person, you will thoroughly enjoy and appreciate unit conversions. This video is actually part of a 3-part series. This first video offers us a brief introduction into units and their importance. The second part of the video will teach you how to manipulate units and basically how to do simple conversions. The third video in the series will get a little more advanced and just basically tackle a couple of more difficult 2-part problems. So by the end of it all, you should have a very good appreciation of units, what they are, why they're important, and how to convert between them. So the first thing we want to look at is what are units and why are they important? And units generally give us some idea of the magnitude of the thing we are describing. And suppose someone asked you how far a store was, and you said, oh, the store is 7. Well, immediately that seems a little odd. 7 what? 7 minutes walking, 7 minutes driving, 7 miles, 7 kilometers, 7 yards, 7 nautical miles, 7 light years, 7 millimeters, whatever. Generally, we need some unit. Some of those obviously wouldn't be appropriate for the distance to a store, but without a unit, your number or your description is generally very vague. Units are going to tell us or tell the person you're talking to, it's going to give that person some idea of the magnitude of what you're describing. Likewise, if I said the temperature outside is 30, is it hot or cold outside? Well, if you're in the United States, you're probably used to the Fahrenheit scale, so 30 is going to be cold. But if I was describing the temperature and the Celsius scale, 30 degrees would be actually quite warm. So generally, 30 is 30 degrees outside. Most of the world uses the Celsius scale. They don't use the same scale that's used in America. So 30 degrees isn't really it's not really good terminology to use. We generally want to apply a unit to whatever we're using, and especially so in science. So if we're sharing data or collaborating, each party involved knows what we're talking about. And obviously the picture down here, you see a skinny individual and a plump individual. And let's suppose you were talking to someone online and you never met them before. Friends of yours are trying to hook you up, and you were asking them questions about their weight or their height or their hair color or their interests, whatever it is. And the person said, well, I weigh 160. And you might assume they weigh 160 pounds, like this gentleman right here. But if this person was maybe from Europe and they didn't use pounds, that 160 might very easily be kilograms, and this person would be closer to 350 pounds and would look like the gentleman on the right. So units generally give you an idea of what you're talking about. A number by itself is not very useful, especially not in science. Oop, a little far. Converting units is very important. And if we look at this map here, notice all the countries in gray. Those are all the countries that do not use the English system or the American system that we use now. All these other countries are basically using metric or something called the standard international system. And what that means is we measure distance in feet or miles in the United States. Everywhere else, they're using meters, kilometers. They're using the metric system. We take temperature and the Fahrenheit scale. They use Celsius or degrees centigrade. So if you were to go over to Europe and cook a lasagna and you were to set the oven to 350, because obviously you want to cook lasagna at around 350 degrees, maybe 400. If you set that oven in Europe to 350, well, congratulations, you would make a big pile of coal for all your dinner guests because you would pretty much burn the crap out of it because that oven's going to be set to Celsius, not Fahrenheit. Likewise, if you went to Canada and upon crossing the border, you saw, oh, look, the speed limit's 100 miles an hour. These Canadians are crazy, eh? So you decide to, crank the music, bump, 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 and you're just going along 97 miles an hour. All of a sudden, woo, 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 you're getting pulled over. And officer, what's the problem? I was going under the speed limit. Well, this isn't 100 miles an hour. It's 100 kilometers an hour. So hopefully, at this point, you get arrested, fined, tased, and thoroughly searched for narcotics possessions. But other than that, you should be fine. Sometimes conversion is very important in cooking. You may need to put a couple tablespoons of something. Maybe you can't find the tablespoon measure. You got to convert from teaspoons to tablespoons or liquid water. Maybe you like a chef online and he's from Europe, and instead of using ounces, he's going to use milliliters. Or instead of using temperatures, he's going to tell you to cook things in Celsius instead of Fahrenheit. That happens sometimes because the rest of the world, as you can see, uses a different system of units than we do. And of course, collaboration. We live in a global world today where you may have friends that maybe you never met in person or that you do business with all over the world, and they may use a different system of measurements than you. So some confusion can arise when you are communicating or talking, especially for scientists. Scientists across the world need to make sure they are using the same set of units so that we know what we're describing is being done so in a consistent fashion. And let's look at some major conversion errors that have resulted throughout history in lieu of improper use of units. We're going to look at the NASA Mars Climate Orbiter, something called the Gimli Glider, roller coaster ride in Tokyo that shut down, a giant escaping tortoise, there's a Korean air crash, some very expensive rice, and medical overdose errors, which are going to be huge in terms of units. So the first thing we want to look at is the Mars Climate Orbiter. Well, we all know what NASA is, and NASA was launching an orbiter. They wanted this spaceship to orbit Mars and basically learn about its climate so we can look at its history, see about water there in the past, the potential for life. Kind of glimpsing Mars will give us, the past of Mars will give us a glimpse into Earth in the same time period. So we want to study Mars to know about Earth, to know about life. And NASA basically had two companies. One company was handling the software, one company is handling the hardware. Well, what happened was when you apply thrust to move your spaceship, one group programmed their thing to use pounds of force, and one group was using newtons for their thrust. And what happened was they ended up, instead of orbiting the planet, too much thrust was given, and this satellite basically orbited too close to the planet, the red line. It ended up being much closer than it wanted to be. And the closer you get to a planet, the thicker the atmosphere is due to gravitational effects. And this thing ended up burning up in the Martian atmosphere. And it only cost a whopping $125. I mean, $1,250. I mean, $12,500. No, it was $125,000. I don't know, we'll cut the long story short. It was actually $125 million. This spaceship, due to a unit conversion error, and it cost $125 million, burned up in the Martian atmosphere. Completely useless. And I think people spent years of work on this, their lives it was not a good time. And I believe overall the total mission cost, counting everything, might have been in excess of $300 million. So a simple unit conversion error. One group used pounds, the other group was using newtons. Imagine mixing up feet and centimeters and costing $125 million. That's essentially what happened here. Pretty embarrassing time for NASA. It was otherwise awesome. We have something called the Gimli Glider, and I believe this was 1983, Air Canada. Well, there was a system malfunction, so when the plane had its layover, the fuel had to be filled up manually, and somebody did a manual calculation of how much fuel the plane needed to make the rest of its journey. And they mixed up pounds with kilograms. If you understand pounds and kilograms, you know that 1 kilogram is actually 2.2 pounds. So if you put 20 pounds of fuel in instead of 20 kilograms, you're actually putting like over 2 times less than the amount of fuel you'll need. So imagine you're flying along at 40,000 feet above the ground where everything looks like ants and tiny little dots, and all of a sudden you run out of fuel. That is not a fun time. It's kind of a Wile E. Coyote moment, though my students are probably too young to even know who that is. Fortunately, in this case, the pilot was able to basically glide the plane in without fuel. Crash landed it on an airstrip he knew about. It was kind of a miraculous landing. It was very fortunate that no one got hurt. And only one person got hurt in this. And that was sliding down the slide to get off the emergency exit. So imagine that a plane runs out of fuel at 40,000 feet above the ground, roughly 8 miles ish, and no one actually gets hurt until they actually get off the plane sliding down. But fortunately, no one is hurt. But again, unit conversion errors. Somebody mixed up pounds and kilograms. Roller coaster derailment. There was Space Mountain in Tokyo. This is not a picture of that. It's just a picture of people stuck on a roller coaster. Yes, this does happen. I know we all love roller coasters. Whee! Going up and down and those changes in kinetic and potential energy. Awesome. But in Space Mountain, a roller coaster derailed right towards the end. It came off the tracks. Why? Because at some point in the history, they decided to change the design schematics to metric, and there was a size miscalculation. The washers or the bolts they bought were just off by a millimeter, and it ended up. That's what happened. The roller coaster was not built properly, or it was not maintained properly. The bolts were the wrong size. The roller coaster derailed. Had to shut down for a while. That's what the investigation found. Basic metric conversion error, kind of a Final Destination 5 scene happening. Very frightening. The 250-pound giant turtle. The turtle who was too big for his home. I believe LA Zoo had a basically 250-kilogram giant sea turtle. They sent it on loan to a college, and the college had to build a pen for it. And it was like, well, how much does the turtle weigh? Oh, it weighs 250. So the college assumed that they meant pounds instead of kilograms. And 250 kilograms is, well, really 550 pounds. It's closer to 550, not 250 pounds. So this turtle had a home that was not adequate for its strength. This is like a gargantuan turtle, just a beast all around. Knocked its pen down, it escaped, at a whopping speed of 0 miles an hour. I'm sure they found it and everything worked out. But again, unit conversion errors. There's a story of some business, some trade going on, a little marketing. A Japanese guy was buying rice from an American vendor, and the American vendor, quoted him a price of 39 cents. The Japanese guy was elated. Oh, wow, I'm getting rice for 39 cents a kilogram? This is amazing. So, yeah, I'll take 10 million pounds of it. But the American guy was thinking 39 cents per pound, not kilogram. And again, there are 2.2 pounds in a kilogram. So, there's a price differential of over 2 times as much. Long story short, I think the American guy ended up selling him the rice at a loss, or basically not making profit to ensure long-lasting business in other avenues. But again, a simple communication error between two people on different continents, different parts of the globe, using different system of units. So again, unit conversion errors are going to be important in many different walks of life, not just science, but business, communications, and other things of that nature. And medication overdose errors, these are absolutely huge. The FDA has estimated that medication errors cause a death a day and injure over 1 million people a year. That is just alarming. It's insane. These are preventable injuries. There was another study that showed 2 out of 100 people gets dosage information mixed up in the hospital. Out of every 100 people that visit, 2 of them are given incorrect dosages. And unit conversion errors are a big part of this. People are dying. People are getting sick due to unit conversion errors. These are preventable, simple mathematics. But to be human is to err, but we're trying to fix these things. So it's very important, especially for people in pharmacy or the medical profession. We've got to watch our units. We've got to watch our labels. And anyone going in those fields, it's absolutely of pivotal importance to understand units and to be very careful with what you're using, what you're converting. And let's look at 5 examples of what happens when we don't use units. So these are going to be some problems we're going to read, and they're going to associate themselves with 5 different areas, and we're going to see the importance of units in everyday life. So we have a question dealing with medication. A typical adult prescription of the painkiller acetaminophen with codeine in it is 500 blank. And we have some choices: tablets, grams, milligrams, ounces, milliliters. And what this basically is basically Tylenol with codeine. So what is a typical adult prescription of Tylenol? 500 what? Do you think it's tablets? That doesn't make sense. Do you think you should take 500 Tylenol pills? That is like alarmingly bad. Like, I don't think that's even remotely close. So that's not an answer. Milliliters, a liter is generally a measure of a liquid, like 2-liter bottle of soda, 3 liters. And so if a Tylenol is coming in a pill form, probably not going to use a liquid measurement. So we have 3 choices left: B, C, and D. If you know anything about ounces, and 16 ounces is equal to a pound. So if you have 500 ounces of something, you have close to 31 pounds. Do you think you should take 31 pounds of Tylenol? I hope you say no. Definitely don't want to take 31 pounds of Tylenol. If you think you should take 31 pounds of Tylenol, you probably had Mr. Zappone last year as a science teacher. Ha ha. So we have two choices, milligrams or grams. And again, if you know anything about a gram, 500 grams is going to be roughly half, or not roughly, actually half of a kilogram. And that's going to be roughly a pound, 1.1 pounds. And again, taking 1.1 pounds of Tylenol, that would be a very bad idea. We don't want to do that. So sometimes this is how the process of science works. You might not know the unit for something, but you might be able to eliminate it. I always tell my students that use a test against itself if you have to. Sometimes it scores you a few extra points, especially when they're multiple choice. So milligrams is probably most likely the correct answer here. But what are some consequences of being incorrect? That's really what we're looking at. What happens if you overdose on Tylenol? Well, cold and clammy skin, extreme sleepiness, progression to stupor, or coma. Maybe that explains something about my students. General bodily discomfort, heart attack, kidney failure, liver failure, low blood pressure, muscle weakness, nausea, slow heartbeat, sweating, and vomiting. So generally, overdosing on prescription medicine is a bad idea. And again, another example. Let's look at the speed limit. And we kind of touched on this earlier. The speed limit in Canada in a school zone is 30 blank miles an hour, kilometers an hour, feet per second, meters per second, or yards per second. We kind of mentioned earlier that the speed limit in Canada is given in kilometers per hour. That's why you have a maximum speed of 100 kilometers per hour. And the difference between kilometers and miles is a ratio of 1.6. But generally 30 kilometers an hour. If you're going 30 miles an hour, you'd be going a lot faster. You'd be going closer to 50 miles an hour in the school zone. And what are the consequences of being incorrect here? If you were speeding in a school zone, well, accident, loss of life, or a significant fine. So generally, we want to be conscious of our units. Even something simple like bicycle tire pressure. What if you buy a tire gauge or a pump and it has a gauge on it and you don't understand what that gauge is measuring in? And someone says that, yeah, you should put air pressure in your mountain bike. The air pressure should be 60 blank. 60 what? Pascals, kilopascals, pounds per square inch, or PSI, so or millimeters of mercury. So if you don't know 60 what and you put 60 of the wrong unit in, your tire could be underinflated or overinflated. And generally, that's not going to be safe for you, especially if you are actually mountain biking down mountains with rocks and steep embankments. Consequences of being incorrect, you can guess. Uninflated tires. Underinflated tires make puncture more easily. They'll wear out faster. They're more difficult to pedal. They don't stop as effectively, so it's harder to brake. Overinflated tires may blow out. In the end, improperly inflated tires increase the chances of serious injury, loss of life. So again, unit conversion errors. Dietetics. Many physicians recommend that pregnant women take no more than 10,000 blank of vitamin A per day. So pregnant women, should they be taking no more than 10,000 grams, milligrams, ounces, international units, or microliters? Well, 10,000 grams is essentially going to be 10 kilograms or 22 pounds. Is that a good recommendation? Don't take more than 22 pounds of vitamin. No, obviously that's wrong. So you can do the same thing we did with the first one. You can eliminate some of these. You can eliminate ounces. You can eliminate grams and so forth. But the point of this is what happens if you take too much vitamin A, if you confuse the units. Well, there's birth defects. We don't want that for our children. Dry skin, scaly skin, headaches, fatigue, painful bones, and a loss of appetite, which obviously never happened to me before. And the final one we're going to look at is food storage, just to hit another walk of life. Food scientists recommend that produce companies store apples, cherries, apricots, and most berries at 2 blank. Is it Fahrenheit, Kelvin, Celsius, Rankine, or Reamer? Not even sure if I pronounced that right. Reamer. But if you store food improperly, we kind of know what's going to happen. It's going to go bad, or it might ripen too fast, or a lot of things are going to happen. Storing these fruits at too high a temperature will result in ethylene production and early ripening. Storing them at too low a temperature will damage the integrity of the fruit. So again, if you're working for a big business or whatever, we want to make sure we're storing our produce, our fruit, our meat, our fishes, whatever we're storing, got to be at the right temperature, and we got to make sure that we are using the appropriate units so that our fridge is registering what it's supposed to be. If it's 30 centigrade, then it needs to be 30 centigrade, not 30 Fahrenheit. It's going to be a big difference between the different temperature scales. This video is just about coming down to a close. I have just a brief assignment at the end. I just wanted to mention some resources and give thanks to the source book for teaching science. I kind of borrowed lots of material from Norman Herr. That's an excellent book, excellent series. I recommend it for teachers. Some of these questions were taken right from there. For the metric mix-ups, there's Colorado State University, USMA. There's a link there. They had a nice description of a bunch of metric mix-ups, like the turtle, some Olympic records, and a lot of things. And obviously, all the images you see in here are basically taken from Google Images. And my students, your assignment, simple, your notebook. Why is it essential that all measurements be accompanied by units? We've had quite a few slides and many minutes of this being discussed. And then you have two other things you need to do. First one's a question. Second one is where you're going to create something. Individuals who travel to regions of the world with poor sanitation are warned to filter water before drinking it to remove deadly waterborne pathogens that cause diseases such as cholera or typhoid. If you were traveling in a region known to have a polluted water supply, would you drink water that your host said had to be heated or had been heated to 100 degrees for 5 minutes? Explain your answer. So your host tells you, yes, we heated the water to 100 degrees for 5 minutes. Don't worry, it's safe. Do you want to drink it? Do you have any questions for your host? I hope you do. And we saw 5 examples of what happens when we don't use units. Now it's your turn to create a scenario. Develop a hypothetical problem that may arise when units are omitted. You can do it in a field such as sportscasting, international trade, or any area of your choice. Just come up with a mock situation where a deal gone bad or something where unit conversion errors were to blame. Include a consequences of being incorrect section. So what happens when you mix up your units? So develop that scenario, and we'll probably work on this in class since you're watching this video at home. This is Mr. Zapone, and I hope you enjoyed this presentation. I'm out.